Friends, welcome back to my YouTube channel. In this class, I am going to discuss three more problems of chapter 7 of PKNAG's Engineering Thermodynamics, which is based upon the concept of entropy and entropy generation. And before starting, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. Let's get started. A body with the equation of state, question number 7.13, a body with the equation of state U is equal to Ct. In fact, internal energy is equal to product of heat capacity and temperature. Where C is its heat capacity is heated from temperature T1 to T2 by a series of reservoirs ranging from T1 to T2. And this is in fact a process of reversible heating, because the heating process takes place through infinitesimal temperature difference. Because when heat transfer takes place through finite temperature difference, then that process is an irreversible process. So this is a case of reversible process when the body is heated from temperature T1 to T2 by coming in contact with a series of reservoirs. The body is then brought back to its initial state by contact with a single reservoir at temperature T1. This is not a reversible process of heating. When the body comes back to initial temperature T1 by coming in contact with only a single reservoir, that is not a case of reversible heating. First one is reversible heating process, and the return process is not a reversible heating process. That is in fact an irreversible process, because the temperature difference is finite here. Calculate the changes of entropy of the body and of the reservoirs. What is the total change in entropy of the whole system? That means we have to calculate the entropy change of universe. Universe is here a composite system which consists of two subsystems, that is system and reservoir, or body or reservoir. And that is the second part of the question, is that if the initial heating were accomplished merely by bringing the body into contact with a single reservoir at T2, what would be the various entropy changes be? That means if the initial process were an irreversible heating process, then what would be entropy? In this first part, when the body moves from temperature T1 to T2, it is a reversible heating process because it comes into contact with a series of reservoirs, so that the temperature difference during each of the heating process is infinitesimal. And the second return path, when the temperature of the body comes back to its initial temperature T1, that is an irreversible heating process. So first we will calculate the total entropy change or entropy change of universe in the first part, and then for the second part we will calculate the entropy change of universe and then compare. You see, this is your U is equal to Ct, and the temperature of the body increases from T1 to T2 by coming in contact with a series of reservoirs. So in fact T2 is greater than T1. So delta S1 in this case, when the temperature of body increases from T1 to T2, where the temperature of the reservoir is this is the higher temperature, and so delta S1 is equal to delta S of, in fact the reservoir temperature is at T2. So delta S TR plus delta S body. Body is heated from T1 to T2 by coming in contact with the series of reservoirs, and the temperature of the last reservoir being T2. In this case, this is 0. In fact, all the heating processes, this process consists of a series of heat exchanges between the body temperature and reservoir temperature, and each of the heating process, the temperature difference is infinitesimal, very small, so that heating process can be considered as a reversible process. So in that case, no entropy change will take place, because that is a reversible heat transfer process. So no, there will be no change in entropy. So delta S TR will be 0 and delta S body will also be 0, because the temperature will not change here. In fact, that is a reversible heating process. So delta S for reversible, delta S universe, in fact, for a reversible case is 0. In fact, the delta S universe, according to principle of increase of entropy, is greater than or equal to 0, and it is equal to 0 for reversible process. And this is a case of reversible process only, because the temperature of body increases from T1 to T2 through by coming in contact with a series of reservoirs, and this is a reversible heating process. And in case of reversible process, delta S universe, or total change in universe, total change during the process of entropy during the process, you can say, is 0. But what is the entropy change of universe when the reverse or return process takes place? So this is, suppose the body temperature now goes down from T2 to T1. Initially the body was at temperature T1, and once it is heated to T2, and then during the return process, during the reverse process, when the body temperature decreases from T2 to T1, and the reservoir is at, this is TER, thermal energy reservoir, is at temperature T1. And so obviously, how can the temperature of body decrease from T2 to T1? Only by giving away heat to the TER, or thermal energy reservoir. So what is the heat rejected by this body while coming back from temperature T2 to initial temperature T1? So heat rejected by this body is C, heat capacity, that is nothing but product of mass and specific heat, is equal to C multiplied by T2 minus T1. In fact, mass into small c, that is specific heat, into delta T, mc delta T. So this is the heat rejected by the body to the reservoir. So delta STER, thermal energy reservoir, is nothing but this heat is added to the reservoir. So this will be, plus sign will be put before Q. So Q, and temperature of reservoir does not change no matter whatever heat you may supply to it. So the temperature of reservoir will remain constant at T1, that is C T2 minus T1 divided by T1. And in this case, delta S of body, because the body temperature decreases from T2 to T1, so delta S is nothing but mc dt upon T, and but mc is your capital C, heat capacity, so that is C dt upon T, and initial temperature in this case is T2, final temperature is T1, because the temperature of body decreases from T2 to T1. So this, on integrating, C ln T, limit is from T2 to T1. This is equal to C ln T1 upon T2. This is the delta S of body. So total change in entropy, delta S total, is equal to delta S of reservoir plus delta S of body. So delta S of reservoir is C T2 minus T1 divided by T1 plus C ln T1 upon T2. In fact, this total change in entropy is same as delta S universe during the reverse process. Delta S universe during the reverse process. So if you calculate the total change in entropy of universe during that whole cycle, in the first process, the temperature of body increases from T1 to T2. In the second process, the temperature of body decreases from T2 to T1. So obviously this constitutes a cycle, and the first part of the cycle is an irreversible process, and the second part is reversible process. So first part is reversible process and second part is irreversible process. So if you calculate the total change in entropy during this whole during this set of two processes, that will be only this much, because during the first process change in entropy is 0. So C T2 minus T1 by T1 plus C ln T1 upon T2. And suppose now we will take the case of second case, when the first process is also an irreversible heating process, that is given in the question. You see, if the initial heating were accomplished merely by bringing the body into contact with a single reservoir at T2, so body is at temperature T1 and reservoir is at temperature T2, so the temperature of body increases by coming in contact with a single reservoir that is at temperature T2, which is greater than T1. That this is a case of an irreversible heating process. If it had come in contact with infinite number of reservoirs before getting heated to temperature T2, then it would have been a reversible heating process, because the infinitesimal temperature difference would be present in that case. But in this case, the temperature difference is finite, and so when heat transfer takes place through finite temperature difference, it is a case of an irreversible process. So you see here, during the first process, when the body temperature increases from T1 to T2, you see TER is at temperature T2 and body's temperature is T1, and by getting heat from this, and since T2 is greater than T1, obviously heat will flow from reservoir to body, and by getting the heat coming from this high temperature reservoir, its temperature will increase. So in this case, during the first part of the process, when the body temperature increases from T1 to T2 by coming in contact with a single reservoir, what will be the delta S1? That will be delta S body plus delta S TER, and this is nothing but, you see, delta S body is nothing but C ln T2 by T1, because the body temperature increases from T1 to T2, plus delta S TER will be the heat rejected by the TER, that is minus sign will be put, minus C T2 minus T1. What is the amount of heat rejected by TER here? It is the same as heat accepted by this body, or heat taken away by this body. So this is C multiplied by T2 minus T1, and for reservoir it will minus sign will be put, because heat is rejected by the reservoir and the temperature of reservoir remains constant at T2. So now this becomes C T1 minus T2 divided by T2 plus C ln T2 by T1. This is for fast process, when the temperature of body increases from T1 to T2. And as far as the second part is concerned, when the body's the temperature of body once again comes back to initial temperature T1, the change in entropy would remain the same as we have calculated in the previous case, because here only the difference is that initial process here was an irreversible case, was a reversible case, and in this case it is a reversible case, irreversible case. Here it was first process was reversible, here in this case it is irreversible. Otherwise all other processes, the second process remains same for both the cases. So change in entropy, whatever we have calculated here in the second process, when the temperature of body comes back to its initial temperature, that is T1, the change in entropy we had calculated is this was this much. For second process this will remain the same, delta S2. This is for the reverse process, when the temperature of body comes back from T2 to T1, that is its initial temperature, delta S2 will be the same as it was in the earlier case. So that is C T2 minus T1 by T2 plus C ln T1 by T2. And if you add delta S total, if you calculate delta S total for the whole cycle, this would be delta S1 plus delta S2, and this would be, you see, C ln T2 by T1 plus C T1 minus T2 divided by T2 plus C ln T1 by T2 plus C T2 minus T1 divided by T2, and these two cancel out because this is negative of this one. Ln T2 by T1 is negative of ln T1 by T2. So these two terms cancel out. Now these two terms remaining, and this becomes, you see, C T2 minus T1 multiplied by T2, sorry, this is C T1 minus T2 divided by C T2 minus T1 by T2, and another term is one is T1 and other one is T2. So on being added, this becomes C T2 minus T1 multiplied by T2 minus T1 divided by T1 T2, and this becomes C T2 minus T1 whole square divided by T1 T2. So in the next problem, that is 7.14, a body of finite mass is originally at temperature T1. You see, a body of finite mass is originally at temperature T1, which is higher than that of a reservoir at temperature T2. Suppose an engine operates in a cycle between the body and reservoir until it lowers the temperature of body from T1 to T2, thus extracting heat Q from the body. So initially the body temperature is at T1. Body temperature is at T1, which is higher than that of a reservoir. And in case of a heat engine, there are in fact two reservoirs, one is source and sink. But in this case, there is a higher temperature body, finite body. And on removing heat from a body, its temperature will go down. And once the temperature of the body reaches T2, the process stops and the engine stops performing work. So thus extracting heat Q from the body. If the engine does work W, then it will reject Q minus W to the reservoir at T2. Reservoir temperature is at T2. Applying entropy principle, prove that maximum work obtainable is this much, W max is this much, and where S1 minus S2 is the entropy decrease of body. If the body is maintained at constant volume, having Cv is this much, and T1, T2 are given, determine maximum work obtainable. In the second part only, we will put numerical values to this expression, and we will be able to find the answer. So first we have to find out the maximum work obtainable by applying the principle of entropy, principle of increase of entropy, or simply the entropy principle, whatever you can say. So here see, this is body. The body temperature of the body is finite. Sorry, the body is a finite body. It's not an infinite body. It's body with finite heat capacity, and its temperature will go down once it rejects heat. Suppose this is the amount of heat rejected, by the body Q, and suppose this is heat engine. Clockwise device, work producing device, and W is the work produced by this engine. And if this is the heat, Q is heat supplied to the engine and W is the work produced, then heat rejected to the reservoir is Q minus W, and reservoir is at temperature TER, is at temperature T. So you see, delta S body is, in fact, change in entropy of the body is S2 minus S1. Change in entropy of the body. This is the entropy of body at state 2, and the entropy of body at state 1 is nothing but C dt upon T, del cube, d cut cube, integral of d cut q by T, and this is nothing but heat capacity. So dq is C dt, unintegrating, initial temperature is T1 and final temperature is T2. Since this is a finite body and this whole process will continue, this engine will continue to produce work only up to the point when the temperature of body reaches the temperature of reservoir. So this temperature is the reservoir temperature. So C dt, this is equal to, in fact this is Cv, specific heat at heat capacity at constant volume. This is Cv ln T2 by T1, and you see the delta S of TER. So thermal energy reservoir का change in entropy होता है heat added to this reservoir divided by temperature. Because the temperature of reservoir does not change with the addition or removal of heat, here the only the temperature remains constant in the expression. So you see delta S TR is nothing but Q minus, no integration is required, Q minus W divided by T2. And delta S of heat engine, there are three parts, one is body, another is reservoir, and third one is the heat engine. And heat engine is always, delta S of heat engine is always 0, because the heat engine completes a cyclic process, and the cyclic integral of any property is 0, and entropy is a property. So delta S universe equal to 0 for reversible process, because it is greater than 0 for irreversible process, and it can never be less than 0, and equal to 0 for reversible process. And for any reversible process, work produced is maximum. In this case, work produced will be maximum. This work will be maximum only when all the processes executed by these three parts, or all the processes that take place within this system are reversible process. Then only the work produced will be maximum. So delta S universe is equal to 0 for reversible process, and for maximum work, all the processes are to, for maximum work, all processes are got to be reversible. All processes are reversible. All processes are got to be reversible. So then our what will be the expression for delta S universe equal to 0? Delta S body and plus delta S TR, because the heat engine, change in entropy of heat engine is 0. So now Q minus W divided by T2 plus Cv ln T2 divided by T1 equal to 0 for reversible case. Or I can write Q minus W by T2. This is Cbl and T2 by T1 is nothing but S2 minus S1. This is entropy of the body at second state, and this is in fact the final state, and this is the entropy of body at the initial state. This is 0 for reversible process. Or I can say Q minus W divided by T2 is equal to S1 minus S2. Or Q minus W is equal to T2 multiplied by S1 minus S2. So, or Q minus T2 S1 multiplied by S1 minus S2 is equal to W. And this W is maximum, or I can say W max. This is because this is the expression for reversible process, and in reversible process work produced is maximum. So W max is nothing but Q minus T2 multiplied by S1 minus S2, and this S1 minus S2 is nothing but entropy decrease of the body. Entropy decrease of the body. And if you want to calculate this, Q is nothing but Cv T1 minus T2. So because you see this heat rejected by the body is product of heat capacity at constant volume Cb multiplied by temperature, decrease in temperature T1 minus T2. So this is equal to Cb T1 minus T2 minus T2 S1 minus S2. And in the second part, just numerical values are given, and we have to put the numerical values to find out the maximum work obtainable. So CB is given. So this is equal to CB is given, or you can further simplify this. This is equal to CB T1 minus T2 plus T2 S2 minus S1, and this is equal to CB T1 minus T2 plus T2 CB ln T2 by T1 S2 minus S1. This is equal to CB, taking CB common, T1 minus T2 and minus T2, because you see ln T1 divided by T2, because ln T1 by T2 is nothing but minus of T2 by T1. This is the final expression, and if you put the given numerical values, we can find out the maximum work obtainable. This is equal to, in place of CB I will write 8.4, because it is given in the question. You see CB is 8.4 kilojoule per Kelvin, heat capacity at constant volume, multiplied by T1 is given, T1 is given to be 373 and T2 is 303 Kelvin. T1 is 373, T2 is 303. You see, this is 373 minus 303 minus 303 ln 373 divided by 303. This is the final expression. These terms are within the bracket, and the whole answer will be multiplied by 8.4 to find out the maximum work, and this is coming out to be 58.99 kilojoule maximum work obtainable. This is the maximum work obtainable. And in the next question, that is question number 15. Question number 15 is like this. You see, each of three identical bodies satisfy the equation U equal to Ct, where C is heat capacity of each of bodies. Their initial temperatures are 200 Kelvin, 250 Kelvin and 540 Kelvin. If C is equal to 8.4 kilojoule per Kelvin, what is the maximum amount of work that can be extracted in a process in which these bodies are brought to a final common temperature? So there are three bodies in fact, and suppose they are having T1, suppose T1 is 200 Kelvin, T2 is 250 Kelvin and T3 is 540 Kelvin, and U equal to Ct is given and C is equal to 8.4 kilojoule per Kelvin. Suppose first initially we will take the directions arbitrarily, and suppose there are three bodies and this body is having temperature T2 suppose, and it is coming to the final temperature is suppose T2 is decreasing to actually T, and this is giving away heat to, suppose initially we arbitrarily take the directions and finally we will see whether the directions we have assumed are correct or not. Suppose heat engine is there which is extracting heat from T2, that means the temperature of this body is decreasing according to the assumed directions, and again this is suppose T3, and this is also coming to the common temperature T by giving away heat to the heat engine, that means its temperature is decreasing. T3 is decreasing to T and T2 is decreasing to T because both are giving away heat to heat engine. And then this is the third body T1 which is also coming to the final common temperature T, that means it is getting heat, and both these are giving away heat and this body is gaining heat from the heat engine, that means this T1 is less than T2 and T1 is increasing to T2 just by addition of heat. So, and since it is given that what is the maximum amount of work, so for maximum work this delta S universe has to be 0, because for maximum work all the processes are to be reversible, and so delta S universe has to be 0. Delta S universe has to be 0 for maximum work. It is given that for maximum work nikalo, you have to calculate the maximum amount of work that can be extracted. So for maximum work all the processes are to be reversible, and according to the principle of increase of entropy delta S universe has to be 0. So first we have to calculate the change in entropy of these three bodies. So delta S1 is equal to ClN T upon T1, delta S2 equal to ClN T upon T2, delta S3 is ClN, this is capital C, heat capacity, ClN T upon T3. So delta S universe, and this delta S of heat engine is always 0, because this completes a cyclic process, and cyclic integral of any property, that is entropy, is also a property, and cyclic integral of any property is 0. So delta S universe is 0, that is delta S1 plus delta S2 plus delta S3 is equal to 0, or ClN T upon T1 plus ClN T upon T2 plus ClN T upon T3 equal to 0. Or I can take C common, and this becomes ln T upon T1 plus ln T upon T2 plus ln T upon T3 equal to 0. But you see, C cannot be 0. That means how can this whole term be 0? Only when this term is 0. Or ln T upon T1 plus ln T upon T2 plus ln T upon T3 equal to 0. So this can be further simplified as ln T cube divided by T1, T2, T3 equal to 0, and which is nothing but ln 1, or T cube by T1, T2, T3 equal to 1, or T cube equal to T1, T2, T3, or T is equal to cube root of T1, T2, T3. So this is equal to cube root of three temperatures that are given in the question, 200, 250 into 540, that is equal to 300 Kelvin. So T is coming out to be 300 Kelvin. Now you see, T1 will gain heat. Obviously T1 temperature, T1 is 200 Kelvin, but T is coming out to be 300 Kelvin. That means this direction is correct, because T1 is increasing to T1 is 200 Kelvin and increasing to 300 Kelvin. There is no problem in assuming this direction. So whatever direction we have assumed for body 1 or for this body with temperature T1 is correct, but for T2 it is wrong, because T2 is 250 Kelvin and T is coming out to be 300 Kelvin. That means T2 has to gain heat for its temperature to increase from 250 Kelvin to 300 Kelvin. It has to gain heat, but in this case it is losing heat. So this has to be in the other direction. The direction has to be changed. So now the revised diagram will be like this, but again the T3 temperature of T3 is 540 Kelvin, and it is reducing, temperature is reducing to 300 Kelvin, means it is giving away heat, and which is already there. So this is correct. So now the revised diagram will be like this. So this is T3 will be in this side of the heat engine. It will give away heat Q3, and its temperature will go down to T, and heat engine is there. Then suppose this will give away Q1 amount of heat to T1, its temperature will increase, and this will give away Q2 amount of heat to temperature T2, its temperature will also increase. Temperature of these two bodies will increase. Now you see, Q1 we have to calculate. Q1 is C multiplied by T minus T1. So this is the heat added to this body so that its temperature will increase from T1 to T. So what is the amount of heat added to this body? So C T minus final temperature minus initial temperature. This is 8.4 multiplied by 300 minus 200. This is 840 kilojoule. And what about Q2? So Q2 is C multiplied by T minus T2. This is 8.4 multiplied by 300 minus 250, that is 420 kilojoule. Then Q3 is nothing but Q3 is C T3 minus T, because T3 is 540 Kelvin and T is 300 Kelvin. So 8.4 540 minus 300, this is 2016 kilojoule. So heat added to heat engine is 2016 kilojoule and heat rejected is Q1 plus Q2, and this is producing the max work produced. This is the maximum work produced. So what is the heat rejected? If you calculate, Q rejected is equal to Q rejected is Q1 plus Q2, that is 840 plus 420. This is equal to 1260 kilojoule. And the heat added is already calculated, that is 2016 kilojoule. So maximum work produced is nothing but 2016 minus 1260, that is 756 kilojoule. So when all the three bodies are coming to a common temperature of 300 Kelvin, in the delta S universe is equal to 0. That means the maximum work would be obtainable, and that maximum work is nothing but the Q3 minus maximum work is nothing but heat added to the heat engine minus Q1 plus Q2 according to the first law of thermodynamics. Sigma W cycle equal to sigma Q cycle. So this is equal to your 756 kilojoule. So that's all.